I have no idea what we're teaching. No, just kidding. We're going to look at higher order polynomial graphs. Higher order is anything that's 3 or higher. So when I say higher order, I mean the highest degree exponent, 3 or higher, you're going to get these funky looking graphs. Okay? And we've been working on factoring so that we can factor this and get the x-intercepts of these graphs. So what we're going to do today is we're going to notice some other properties you're going to need to know in order to graph these, and then theoretically we can graph them. It's not, I know they look scary, but it's actually going to be pretty straightforward once we kind of draw a bunch with Desmos and stuff. You guys are going to be pro at it. So here's 3 graphs right now. This one is this one. Number 2 is right there. Number 3 is right there. Okay? So there's some writing down there. Let's take a look at what it says. I'll scroll down. So they're all degree 3. Notice the number and value of x-intercepts. So when y equals 0, let's look at them all. How many x-intercepts do we have in the first one? 3, perfect. And the degree is 3. How many x-intercepts here? 3, perfect. And then 3, 1, 2, 3. Okay? So what I'll tell you now, and you can write it in your notes, is the degree tells you the maximum number of x-intercepts. It's the maximum number. So it's not a guarantee that, hey, it's degree 3, there will be 3 x-intercepts. Like in the mental math, I think we saw a question that was degree 3, and I think there was 2 x-intercepts. But it tells you the maximum number. How many y-intercepts do you see in each case? Just 1, okay? So, and that's always the case for all these higher order ones. It'll cross the y-axis somewhere once. And by the way, how do you find the y-intercept? You said x equal to 0. Beautiful, man, you guys are so smart. We did not rehearse this, by the way, that's perfect. Notice the sign and direction of the graph. So when I say the sign, you're going to find out that as we graph more and more of these, it's going to be the sign on the highest power that matters. So just like how the person with the biggest personality takes over a group of people and kind of usually becomes the leader, the highest power usually determines the way the graph is going to like begin and the direction. So, well, that's the trickiest thing to figure out. So let's just look. This one right here, it's a positive, we call it leading coefficient. There's that leader thing again. Of +2, right? So it's +2 x to the 3. And now this graph starts down here, makes this S shape, and ends up here. So the overall direction is, if you think of it like a line, is like that. What kind of sloped line is that?
Positive slope.
It's a positive slope line. So that's interesting. Could be a coincidence. Who knows? Over here, what's the leading coefficient now? -1. So I'm just going to go LC for leading coefficient. I thought there was something funny there. Maybe there was. It's -1. And now look, it's starting over here in quadrant 2, and it's ending over here. What kind of line is that?
Negative.
It's a negatively sloped line. Negative slope line. And I don't know, maybe that matters, maybe it doesn't. It does matter. But we got to see more graphs before we'll see it, I think. Okay, here's another one. So still degree 3, and it's, what's the LC, the leading coefficient?
-3.
-3. And, so it starts over here. It's hard to see. It starts over here, goes like this, ends over here. Is that a negatively sloped line again?
Yeah.
Yeah. So watch out for this. For a degree 3 graph, because the degree matters, for a degree 3 graph, if you have a negative leading coefficient, we call this end behavior, by the way, so where it starts and where it ends, we call it end behavior. It has the same end behavior as a negatively sloped line. Okay, and this one had a positive leading coefficient, and its end behavior was the same as a positively sloped line. And there is something significant there. Okay, last thing, we talk about the relative maximum and minimum. So relative as in like these little, we call this a hill. Maybe I'll erase it so we can actually see for the video. So like if you take like calculus, sometimes they talk about peaks and valleys and stuff. So like this is a valley, this is a peak, and we call that a relative max and a relative min. So generally when a graph changes direction, like we're going like this and then we switch direction and we start going down towards the negative y's, sometimes those points are interesting. You know, it's like, ooh, something's happening there. And usually that'll depend on the context of like the problem. Anyways, so we call those relative minimums and maximums. Okay, they're relative because this graph goes on forever and ever. So like this is not the maximum y value. The maximum y value is infinity. But anyways, that's more setting up for calculus. So I believe you have. Do you have all this in your notes? The blue writing and all that?
Yep.
Yeah. So I basically summarized for you all the things I said. And let's just quickly go through one more time. So the way these graphs look depend on a few factors. Yeah, the highest degree in the polynomial, and that's the max number of x-intercepts. But the actual number of x-intercepts will be between 0 and that maximum number. Whether or not the degree is odd or even, so I didn't quite state it that way, but yeah, if the highest degree is odd or even, it's going to change the shape of the graph, like the end behavior. So we just started noticing all of these are odd degrees, and all of them happen to be 3. So we'll see this more, and we'll come up with some generalizations for that. And whether or not the leading coefficient of the term at the highest degree is positive or negative, these two things go hand in hand for what the end behavior is going to look like. And on the exam, they like to ask you about, like, you know, what's the end behavior of, you know, this polynomial function. Don't sketch it, just tell me what the end behavior is. It's like a 1 or 2 mark question. So by the end of this lesson, you'll be better at being able to tell that, okay? Any questions before we look at some more graphs? Jack, are you excited?
I don't know.
Good, great, good. He said yes. So, on the next page, you basically have, oh boy, this message. Let me just, I must have forgotten to clear the ink. Okay, so here we are. We got these 4 graphs, and I believe if you flip your notes, like I went and labeled them. I got them from Desmos. So take a moment, take a moment on your own to see if you're noticing anything. So really quick, I'm just going to switch to the computer here for a second. So unfortunately you will not be able to see me on camera, but you should be able to hear me. Right here, this is the only thing that matters as far as the shape of the graph. Right, so it's a degree 4, and it's got a negative leading coefficient. Okay? What's the max number of x-intercepts?
4.
So 4. Max x-ins 4. So now, if we go and flip through, normally I would use Desmos, but it takes forever to type them in, so I just got some screenshots. Here's the graph for that first function. So this is I. This is this negative leading coefficient degree 4 graph. So let's see, how many x-intercepts? 4. 1 y-intercept somewhere down here. And now, so the end behavior is, it starts down here in quadrant 3, and it ends down here in quadrant 4. Okay. Let's look at the second one. The second one is basically identical, maybe I can type, except what's the LC? So it's degree 4, and the LC is positive. So still got 4 max x ints. Okay? None of the other numbers matter really. Well, I mean they do, but as far as like what we're gonna notice is, okay, so this was negative leading coefficient, degree 4 graph. Starts and ends down here, quadrants 3 and 4. Positive ends up here in quadrant 1 and 2. If you sort of ignored like all this stuff that's happening in the middle, oh, and look, this one has no x-intercepts. Right? So finally a graph where, you know, instead of having the maximum number, we don't have any x-intercepts. But do you notice how we do still have a y-intercept? Yes. Now if I was to compare this to something you guys did in grade 11, if you ignored all the stuff in the middle, you just had a graph that sort of did some stuff and went like this, what kind of graph would you compare it to?
Negative and positive.
Yes, very good. So amazing, actually. So yeah, it's kind of like a parabola. This is kind of like a parabola. And I wonder, I should just tell you this now. What kind of parabola opens down? Like what would be an equation of a parabola that opens down?
Negative x.
Perfect, like just negative x squared, right? That would be this parabola. But notice how the end behavior is the same. That's interesting. And a parabola that like opens up, that maybe starts at the origin, what would that be? y equals
X squared.
just x squared. Let's compare the leading coefficient. So negative leading coefficient, same end behavior. Okay, even power. This is a degree what graph? Degree 4. So even power graph, even power degree, negative leading coefficient, same end behavior. Let's check if it works over here. Boy, did that get messy, but let's see. I like how I can just touch this board. Don't need the marker. Takes me back to the beginning of smart boards used to. Okay, here we go. Positive leading coefficient, even degree, same end behavior as a degree 4 graph. Okay, not a coincidence. All right? That's what mathematicians do. Like, they notice patterns. And then the hard part that we never do in high school is like, now can you show me that it works for every degree 4 graph? And that's called a proof. Okay? So what we do in high school is we say, look, the proof's been done, it works, and we just show you the pattern. So I have a table at the end of your notes that summarizes everything that we're going to notice. But yeah, as far as end behavior goes, even power degrees have the same end behavior as parabolas. So I'm going to relate it back to that knowledge because you guys are really good at parabolas. Odd powered ones, so if you have an odd power degree, well, guess what? Lines are odd powers, right? Like y equals mx plus b. What's the power on the highest degree x? 1. That's an odd number. So if you have an odd degree, it'll follow the same end behavior as a line. So odd degree, positive leading coefficient, so positively sloped line. So you'll start down here and your graph will end somewhere up here. If it's a negative leading coefficient, it's a negatively sloped line. Start over here, end over here. That's the pattern. So once you put all that stuff together, like you can get the x-intercepts, right? You can easily find your y-intercept by plugging in x equals 0. And then you can figure out the start and end behavior of the graph by looking at the leading coefficient and the degree. You can actually get a sketch of these bad boys. And that's what we do. Does that make sense? Should I just end the video there? It's perfect. Do you like that YouTube? Yeah. Mark Zuckerberg? No, wait, who's the YouTube guy? Alphabets. My kid likes Alphabets, the cereal. Alright. Good? Okay, well then I guess we can just stop the lesson. No, we'll look at a couple more. And then we'll look at the table that summarizes it all. So, let's test our theory. Let's test our theory for these odd degree functions. Okay, odd degree functions. Before we look at them, okay, don't look ahead. If you did already, well, whatever. But don't look at them. Let's predict the end behavior, because if we have a positive leading coefficient here and it's an odd degree, we're expecting the same end behavior as what kind of line? Yes, positively sloped line. So it should start in quadrant 3 and end in quadrant 1. Yeah. So let's see. So I'm going to write it down. I'm so confident that we're going to write this down. Let's use red. So let's see. Degree 5, and then we'll brackets write odd. End behavior. So we're expecting it to, whatever, start in quad 3, end in quad 1, like a positive sloped line. All right. Right there. Okay, let's see. So if this is graph, it says a 1. Is it 1 again? Okay, well let's see. I believe I called it 3. Yeah. So I called this, I don't know if I changed it on your notes, but yeah, we're calling this graph number 3, and we're going to call this graph number 4, okay? So when you go ahead in the notes, here's graph number 3. So you'll notice there are 5 x-intercepts, 1 y, but look, just like a positively sloped line, starts down here in quadrant 3, ends up here in quadrant 1. I think we got this. Now, obviously the other one's right here, but I already wrote it's a negative leading coefficient, right? Odd degree. So we'd expect a negatively sloped line for end behavior, and that's right. Starts up in quadrant 2, ends in quadrant 4. And on the exam, that's the kind of language you can use. You can say, well, the graph will start somewhere in quadrant 2, and then it's going to end somewhere in quadrant 4. There is one other way that they like to describe it, and it's sort of annoying. I'll write it down here for this one graph. they like to use infinities in x and y. So the other way goes like this. So you could say, let's say the graph starts in quadrant 2 and ends in quadrant 4, or you could say this. Get ready. Let's see. I think I need a symbol. Hang on. Do they have an infinity symbol? Insert symbol. Let me know if anybody sees the infinity symbol.
Is there?
Where? On the previous screen?
Yeah, top of it.
Perfect. That's got a line to it. Or is that just my screen? Okay, well, so you would say this. Now this graph goes on forever and ever, so really you should add arrows to it. And on the exam, they are always expecting arrows, but Desmos doesn't do that as far as I know. So these are your negative x values. And imagine this graph keeps extending forever and ever and ever. You're going to keep going down in your x values. Your x values are going to get more and more negative, right? So we say that as x goes to negative infinity, what happens to your y values? They shoot up and get bigger and bigger, so they go to positive infinity. So this is how you would write it for the exam. So you would say, or as x, and then you draw a little arrow thing like that. As x goes to negative infinity. Okay, what's this strike through thing though? That's bothering me. Oh, because I activated. There we go. Okay, that's better. Sorry about that. I'll make this larger. Okay. There's a tiny infinity symbol. So as x goes to negative infinity, y goes to positive infinity. There. And so that describes the start behavior. Now over here, x is getting bigger and bigger. So remember, this graph is going off at a bit of an angle. So if it goes on forever, eventually you're going to go, as x goes to positive infinity, the y values are getting smaller. So we say the y values are going to negative infinity. So as x goes to negative infinity, positive infinity, my bad. As x goes to positive infinity, y goes to negative infinity. Okay? There you have it. So the exam will use either language. If you have like one of those explain questions, you could say this and you would get the grades, or you could state it like this and get the grades. In general, if they're telling you, so if it's the exam telling you something, they will usually use this sort of notation. So you need to know both, okay? Because you need to know like what this means. Questions? Okay. We learned a lot today, I think. That's basically the lesson. So, I mean, I'll show you, it'd be nice, you know, if I could give you guys a laptop and say, oh, you know, make up some functions and see what happens. And you can certainly do it at home. We can do it right now as well. You can just make up a couple and predict what happens. You guys want to do that? Sure. I'll show you the table first. I don't know. What comes next? Oh, well, let's just do this. So I went to the interwebs, and I can even print this for you on a separate piece of paper, but I believe it's in your notes. This is basically a summary. I really like this because I went and I found it somewhere. Maybe it was a textbook. I can't remember, a free online textbook, but some genius basically summarized everything that we covered. So say you got a function p, right? And then this is a fancy way of writing it, like, you know, some coefficient x to the n, and the power goes down by one, goes down by one until we get to x to the 1, and then x to the 0, which is our constant term. That's just a fancy way of writing it. So when they're saying p, they're talking about your polynomial. All right, so degree n and the sign of leading coefficient an as indicated in the following graphs. So if you have an odd degree, like an x to the 3 graph, then we know that we have that n behavior like a positively sloped line if we have a leading coefficient that's positive. Okay, so positive leading coefficient, odd degree, positively sloped line. Maybe you should write positive slope line. Because if you relate it back to something that you've already learned, you're way more likely to remember it. And to this day, I still think of it like this. I'm like, yeah, you know, it's like a positively sloped line because lines are really just y x to the 1, so it's an odd degree, right? There's a connection. This one will be a negatively sloped line. So if you have a negative leading coefficient and an odd degree, your end behavior looks like that. Now I like this graph or this whatever summary because it also has the language that the exam uses, right? So you say, hey, as y goes to positive infinity, so that's this side, x is becoming more and more negative. Do you guys see that? Question?
Is there a reason why part of the graph is like dotted?
Oh, that's a very good question. Because like this is the part of the graph that will vary, right? So they're just saying like in general, like yeah, in general they have sort of this S shape. So yeah, I should have pointed that out. Odd degree graphs in general have this S kind of shape to them, right? How many times they cross the x-axis is going to depend on all the other numbers. Yeah, so that's why they dotted it, because they're like, well, this is the part that could be different. But in general, it's going to go like this, cross the x-axis, do some stuff, cross the y-axis, end off over there. Yeah. Yeah, excuse me, and for the sketch, sometimes people wonder, like, do I need to know the relative max and minimums? And the answer is no. Right? Like you'll get your x-intercepts, you'll get your y-intercept, you'll figure out your end behavior, you'll start down here, and you will connect the dots, and you know it needs to look something like a curvy S shape. All right? So there's that, and then here it is for the even degrees, right? So really briefly, this is going to be positive leading coefficient, looks like a parabola. So looks like a y equals x squared type end behavior, right? So like positive parabola. Or quadratic. I prefer writing with my finger. Okay. This will be like a negative. So like this is like y equals negative x squared for your end behavior. That's a negative leading coefficient, even degree. So just remember what you learned in grade 9 and what you learned in grade 11 for lines and parabolas. And if you remember that, you should technically remember this, and you don't even need to memorize anything. I'm a big fan in math class about not memorizing stuff. Like you can memorize something in a pinch. You're like, you know what? The test is in 4 days. I'm just going to memorize this because I really don't quite get it. Like I'm getting there, but I'm not quite there. Eventually understanding will come. And if you can understand it, then you'll never forget it. Like I remember when I first started teaching grade 12 pre-calc, it had been like 8 or 9 years since I had done grade 12 math. So like I'd done all this university math, which is completely different. And I was like, it's been like 9 years. And then when I was like going over the notes and stuff, I was like, I remembered everything because I actually understood it. And then I feel like it's easier to teach that way too. It's a little bit harder at the beginning, right? But then at the end it gets easier. I don't know if you guys agree with me or not.
You're doing good.
I'm just teaching to an empty room. It's just a lie, everybody. I'm just trying to make it look like for the YouTube people that there's people here. I'm just some crazy wacko in my basement, like teaching math and be like, "Do you guys get it?" And like nobody's there. Throw in like a laugh track or something. It's like I have friends. There's people out there. You guys should do that. You should try to like work on your laugh track, like make it sound like it's a pre-canned laugh track. You know? You like that, Zach? My kid does it. He lines up all his puppets. And then he'll tell them things. Oh yeah, I know. It's like kids are like they sound crazy when you describe them, but it's like that's how they like learn stuff. So he'll have all his puppets lined up and he'll sing them a song.
That's a demonic teacher.
Isn't it crazy? No, it's not. Just wait till you guys have kids, and then you'll like, and then it makes you humble because you're like, well, I used to do that probably then. Like, yeah. Anyways. All right. I don't think there is anything else really. I think if you're looking for a bit more reading, I think I included a link. There's a bit more reading if you didn't quite get it. Pages 1, 2, and 4 from that one. There's 5 pages. Those are the pages that would kind of apply to us. If you're interested, like if you're like, I don't quite get it, maybe you can go home, sit down. Purple Math is a good resource actually. He's like a math professor at some university in the States. And he does a really good job of breaking down complicated topics in ways that like I just can't do. Like he'll have like animated graphics sometimes, or he'll just have, it's a really good website. If you type in like Purple Math and then like a subject, usually he's covered it. So he's done like all the high school stuff. I don't know, he's a genius. Like the way he explains things to me make a lot of sense. So maybe you guys will find it interesting. Yeah, of course. I think we're basically done the lesson. You'll now be able to do exercise 1.3, and we have like 20 minutes. So why don't we do a couple together? See you next time.